Good morning, everybody. And today we're going to start our third installment video of our chemistry series. And today we're going to learn how to calculate the molar mass. But first, I'm here with...
Me, Daniel, and this is my friend Panda.
And we're all here ready to learn. Now, some things you're going to need at home to learn with is going to be one of these. What's this called?
Calculator.
And one of these. What's this called?
Periodic table.
Very good. Now, I know y'all have them at home, so make sure you have them out and ready to go. Are you ready to go?
Yep.
Is Panda ready to go?
Yeah.
I think we're all ready to go. Let's get started. Okay, so we're going to be here trying to learn how we can understand molar mass. And the best way to do that right now is to make sure you absolutely have your periodic table in front of you. I can't stress this enough. I'll wait. Good. Now that you're looking at your periodic table, we can get started. Great. Let's take a closer look at the periodic table. Specifically, I want to start today off with magnesium. Now, you might remember magnesium as the metal in which we set on fire in class, and it had that awesome reaction with our old friend oxygen as it glowed an incredible white light. And magnesium has, a lot of cool properties, namely 2 valence electrons because it's inside the alkaline earth metals group. But today, specifically, we're going to be looking at its atomic mass. That's going to help us understand molar mass quite a bit. So let's take a longer dive into magnesium on the periodic table. So here's your closer look at magnesium. Now we've got the symbol Mg, but down here, the number we really wanted to focus on today was that 24.3. That is the atomic mass of magnesium. But here's the really cool part of it. It also is the molar mass of magnesium. Now, what exactly do I mean by molar mass? Well, let's look at a real-life example of what I'm talking about. So, if 24.3 is the molar mass of magnesium, let's take a dive into our scale. Now, you might remember my scale here. This is from the kitchen when we were baking our bread. Now, if we can see the numbers here a little bit more clearly, it's been zeroed out and we're talking about grams. Now, again, the number we're looking for here, 24.3. So, I just happen to have my spool of magnesium. This is the one you all wanted me to set on fire all at once. Now, in hindsight, glad I didn't, because we can still do this as a demonstration. I'm going to put this whole spool of magnesium on the scale and check it out. It equals 24.3 grams. So, that is the molar mass of magnesium. What is that really telling us? It's telling us the mass of 1 mole of magnesium. If I had 1 mole of magnesium, and remember, that's old Avogadro's number, not to be confused with his brother avocado, but 1 mole of magnesium, that was 6.023 times 10 to the 23rd atoms of Mg. It would weigh exactly 24.3 grams. So this, my friends, is 1 whole mole of magnesium. Holy moly, you knew it was coming. So that's the basics of what a molar mass actually is. when you're looking at the periodic table and you're looking at any given element on that table, the atomic mass is actually telling you how many grams 1 mole of that substance weighs. It's pretty cool, and it's going to help us do a lot of really cool chemistry in the lab when we get there. And I happen to bring my own little personal lab home with me, so I'm going to be doing some demonstrations here shortly using some things like water and salt. And maybe some sugar. We'll wait and see. Okay, let's start off with water. Now, I've got some water from the sink here. To make this a little bit easier for you to see, I'm just going to add a little bit of blue food coloring just for fun. Now, after we've done that, let's give it a quick stir. Let all the molecules get to know one another. Okay. What we're talking about here is water. Now, what if I wanted to see what 1 mole of water looks like? Well, there's an awesome way to do so. Now remember, 1 mole is just measuring an amount. That's 1 mole of anything. You could have a mole of water. You could have a mole of magnesium, as we saw earlier. You could have a mole of just about anything. And if you can't remember all those fun details about the basketballs, a mole of those, or a mole of pennies, you can go back and watch the mole video that we had in our previous chapter. But we know a mole of anything is equal to 6.023 times 10 to the 23rd of that stuff. Now, that's an awful big number. But what we're counting here are atoms and molecules. And if I want to know what a mole of water actually looks like, we can do that with our newly acquired atomic mass, which is actually the molar mass of any element. Now, this is pretty cool. What we've got here is a water molecule. Just one water molecule has 2 hydrogen atoms and 1 oxygen atom. So let's write that down. Hydrogen, and oxygen. Now, a hydrogen atom, if I had a mole of hydrogen, it would equal 1.0079 if you're adding on the periodic table, but we're going to try to make the numbers simple today. It would be 1.00 grams equals 1 mole of hydrogen. Now, I have 2 of them. That's why I wrote them down twice. That's going to equal 1.00 grams is 1 mole of hydrogen atoms. But here's where it gets cool. Oxygen's molar mass is 15.99. I'm going to round that to 16 grams equals 1 mole. So oxygen is going to be 16.00, we're saying ish here, we're rounding it, to grams per 1 mole. So if I just simply add that up, 16 and 1 and 1, we get approximately 18 grams equals 1 mole of H2O. We have a physical number here that we can measure on our real scale, not counting all these atoms up, but using the newly acquired atomic mass, which actually tells you the molar mass of it, to do the calculation. So let's see what that looks like side by side in real time with our water. We'll grab our scale, we'll open it up, make some room here, we'll turn it on, make sure everybody can see it. And what we need to do, again, if we're setting up a real-time scenario, is nothing's on the scale currently. So I'm going to place the vessel on the scale. It weighs something, so we're going to, again, tare it back to 0. Now, my goal here is to pour exactly 18 grams of water into our container. Whenever slightly. Really close here. We're playing with tenths and hundredths. But 18.3, we're going to leave it there for now. But approximately 18 grams of water is equal to 1 mole of water. This whole number right here, Avogadro's number, is how many water molecules are in this container. And the cool thing is the math shows you how it's broken down. 1 gram of that container is hydrogen. Another gram of that container is hydrogen. And the other 16 grams are oxygen. And as they are combined as H2O, it gives us a round number of 18 grams of water is 1 mole of water. That's how you calculate the molar mass. I think this is a pretty cool trick. And what we've got here is a visual. We can actually see what 1 mole of water looks like. And we can compare that to the full cup of water we had before we actually poured it out into our measuring container. But it's just so neat, that huge number. Avogadro's number, 6.023 times 10 to the 23rd power. That's a 6 with 23 spaces of zeros behind it, is how many water molecules we have in this container. Okay, I think it's starting to make a little bit of sense now. We saw what magnesium looks like if we have a mole of it. We saw what water looks like if we have a mole of it. But now let's do something also equally as familiar. Let's talk about salt. You know, the stuff that is made from a highly explosive metal and a very deadly gas. And you mix the two together and it tastes great on French fries. So let's talk about salt. Let's calculate what 1 mole of salt equals in grams. If we're talking about this, we're talking about NaCl as a compound. That's 1 atom of sodium and 1 atom of chlorine to form the whole thing. But now that we know what it's composed of, we can look here to our molar masses and we can do our calculation. We can look at it as we say that 22.99 on the periodic table. I'm going to round it up again just to make life a little bit easier. We've got 23 grams per mole of sodium. And over here, I've got 35.5 grams per mole of chlorine. All we've got to do is add these two numbers together. And when we do, we get 58.5. That's 58.5 grams of salt is going to be equal to 1 mole of NaCl. So now we've got it. We've got a way to calculate for this compound that we're very familiar with. Let's see what it actually looks like. So as far as salt goes, we're looking for 58.5 grams of it to equal 1 mole. Let's put it to the test. We turn our scale on. Now, if we're looking at it closely, we can see that it's already zeroed out. But again, as I put my measuring container on there, it weighs something. So let's tear that. And now we've got it back to all zeros for grams. Let's add our salt. And we came really close there to 1 mole of it. Sprinkle in a few more grains of salt. We should get right around what we're looking for. So we're sitting right around 58.5 grams of salt. So we now have exactly what it looks like to have a mole of salt. And as you can see, it's not that much, but it is visible. One of the things that we've had problems with is trying to visualize. What do you think salt looks like if I had a mole of it? Okay? And now we do. We have a visual. We have what exactly 1 mole of salt weighs, and now we can put that on a scale and see it right before our very eyes. That is 1 mole of sodium chloride. I think we're up for the challenge of 1 more. Now I want you to get out a sheet of paper and something to write with, and periodic table, of course, and let's work one together. So go ahead and write this down. We've got sugar, which is 6 carbons, 12 hydrogens, 6 oxygens. You'll remember this equation from last week when we first started off learning how to do a chemical equation, how it looks and what it looks like. And in this case, we've got 6 carbons, 12 hydrogens, 6 oxygen atoms make up 1 sugar molecule. But I don't want to know what 1 sugar molecule is. I want to know how many grams 1 mole makes. So if I'm doing this calculation, I need to go to my periodic table. And we know that carbon is 12 grams per mole. Hydrogen is 1 gram per mole. And oxygen is 16 grams per mole. But remember, think back to when we did water. We need to account for not 1 mole of carbon, but how many 6 atoms worth or 6 moles of carbon are going to be worth. So for carbon, what we're going to need to do is to, and mathematically what I like to do here is to use parentheses to keep it straight, especially if you're plugging along with a calculator. There are 6 atoms in there, so we're going to do 6 times 12 because we have 12 of them all together. 12 grams per mole. So this tells me atoms from the compound, and this tells me molar mass of 1 of those atoms. So that comes from right here. Okay, the molar mass of carbon is 12 grams per mole, and there are 6 of them. Close parentheses. We're now going to add that to our hydrogen. Our hydrogen has 12 atoms of it, and they all weigh 1 gram per mole. So 12 atoms times 1 gram per mole. Last but not least, our old pal oxygen, we're going to add the 6 atoms of it multiplied by their molar mass, which is 16 grams per mole. 16 grams per mole. So this is representing our carbon. This is representing our hydrogen. And here we have our oxygen. Adding all of these up, remember, this is nothing more than just addition. We're only multiplying because of the proportions of 6 to 12 to 6 here. And when we do all of that, we get a nice, even number of 180 grams per mole. 180 grams per mole. So, what that tells us is that 1 mole of sugar is equal to 180 grams of sugar. So now I know what is also ultimately saying that 6.023 times 10 to the 23rd molecules of sugar is equal to a weight of 180 grams of sugar. Okay, I think we're getting the hang of this right about now. But one thing we want to make sure is that we tie everything back up together so that we look at the first video to the second to this video and make sure that they're cohesive and that they make sense. One way we're going to do that is go back to our tried and true first formula that we started looking at when we were talking about how equations are made, and the one that we spring to after that when we talk about balancing chemical equations. The two gases of hydrogen and oxygen coming together to make water. Let's see how this, calculating molar masses, applies to that same formula. All right, here we are, back where it all began. We've got hydrogen gas plus oxygen gas yields water. We first started this video series talking about the reactants on the left side of the equation yielding the products on the right side of the equation. But there's a huge problem with the way this is being diagrammed, because right now we start with 2 oxygen atoms and we only end up with 1. We needed to fix that, and we learned that fixing it required using a balancing of a chemical equation. What we do is we can't change what molecules are being added or yielded, but we can change the amount of the type of water or the type of gas that's being used. So we would look at this and say that there are 2 parts hydrogen gas plus 1 part oxygen gas would yield 2 parts water. These are our coefficients that we worked on this past week, along with our chemical equation, which we now know the parts of that we learned last week. But here's the interesting side of the tale. These numbers are now, the coefficients are telling us the number of moles of that substance that come into play. And if they're telling us the number of moles, and we now know how to calculate for the molar mass, well, we can actually figure out how much water is being made in this entire process. So what we would look at here is we'd go to our periodic table and we would know a couple of things. We would know that hydrogen is 1.00 grams per mole. All right. And we know that hydrogen gas would therefore equal 2 grams times 2, which would equal 4 grams of hydrogen gas in the use of this equation. Now, oxygen, there's only 1 mole of it because of the coefficient, but oxygen gas, remember oxygen, if we're looking here, is 15.99. I'm going to round that to 16 just to make the math simple. Is number 8016, and we're going to multiply that by 2. So we're getting 16 times 2 gives us 32 grams in this entire set. So what we're looking at is 4 grams of hydrogen gas total, because there's 2 moles of it, right? And then we look at 32 grams of oxygen gas, because there's only 1 mole of it, come together to make 2 moles of water. Now, remember, the water in this case is H2O. And from earlier in the video, we learned that water is approximately 18 grams per mole. Now we would take 18 grams per mole and multiply it by 2. Why 2? Because there's 2 moles of water here. And as we look at this, end up with is a total of 36 grams of water that's produced. Now, let's look and see if what we're seeing makes sense. We are going to end up with 36 grams of water from this reaction. Now we know that because there's 2 moles of water, and over here we know that 1 mole of water is equal to 18 grams, and since we have 2 moles of it, we are looking at 2 times 18. The bottom of the page trickled off there, but what we're looking at is 36 grams of water. Now here's the really cool part. How much hydrogen and oxygen gas did it take to equal the other parts of water? Well, remember, we calculated that 4 grams of hydrogen gas was used, and we added that to 32 grams. Well, wouldn't you know, 32 plus 4 gives us the same number of water that we needed, 36 grams. So now it's not just about balancing the equation. You can start to see how the actual numbers that are being calculated here get us from the reactant side of the equation to the product side of the equation, and that both sides, over here we had 4 grams of hydrogen gas plus 32 grams of water, and our conservation of not only just matter, but mass is conserved. And this is why we need to make sure that we thoroughly understand how to use our calculator and our periodic table to understand why it's important and what this is telling us about calculating molar mass. All right, so we've done some calculations, and I think you now understand a lot better how to, up or down? Up. All right, I think you understand a lot better on how to calculate the molar mass of any chemical, of any compound, or even any element.
Can you
now,
see me doing this?
Any element, like this one, you want to hold this one up for them? Which one is that?
It's S.
For sulfur, right? We also have Ce for cesium. What about this one? It's a V for vanadium. Now, did Panda have fun today?
Yeah.
Did Daniel have fun today?
Yeah.
Now, what do you like to say at the end of these?
Thumbs up if you like this video. Let me do that again. Thumbs up if you like this video.
Well, I hope you enjoyed today's lesson. And as always, Daniel likes to say,
thumbs up if you like this video. Hello. And you like this video, clap.
Ooh, yes, Panda. Yes, Panda. We clap for you. Outstanding.